Turn on. Yeah, my video as well. It's almost 6:30 here.
Okay. Sir, initially I will share my screen 2 minutes, and after that I will give you the option, sir.
How many participants you are expecting, Sandeep?
Sir, nearly 30 plus, sir.
Now you could hear me.
You are expecting?
30 plus, sir.
Third. Okay. Okay. I see. So this is the first time you found the PELS chapter, I assume, right?
Yes, sir. Sir, we have the student branch here. It was established in 2019, sorry.
Okay.
And then this year already we had another SB chapter, student branch chapter of Power and Energy Society.
Mm-hmm.
And this is the second student branch chapter, sir.
I see.
For election.
Okay.
Yeah.
Okay.
And previous one, Power and Energy student branch chapter, recently inaugurated by Professor S.S. Murthy.
I see. Okay. So how far Bhel is from your place?
Sir, it is in Hyderabad.
Oh, so
Yeah.
there's a Bhel, Visakhapatnam.
Yes, and Bangalore also it is. Yes.
Okay. So
Delhi is in Visakhapatnam also, sir.
Yes, Visakhapatnam, Bangalore, and Hyderabad.
Yeah, because the reason I'm asking because this place is very close to Visakhapatnam or not? Like NIT Andhra Pradesh, where it is in
Yes, sir. We are close to Vijayawada.
Vijayawada. Okay.
And actually, but it's on the highway to Chennai to Kolkata highway, and it's nearly from here. It takes 5 hours to Visakhapatnam.
Okay.
Yeah. I welcome Dr. Rajagopal. He's from BHL, sir, and he is also chair of IEEE PELS, IAS, and PES joint chapter of Hyderabad section.
I see. Okay.
Uh,
Nice to meet you, sir. Namaste.
Dr. Brij Singh and Dr. Sandeep. Thank you for inviting me for this session. Namaskaram, sir. Lakshman garu.
Rajagopal garu, good evening.
Good evening. Namaskaram.
Good evening.
Good evening and namaskaram.
Good morning to you, sir.
Good morning, sir.
Namaskar. How is the weather there?
It's very cold. Let me tell you, outside maybe I live in the coldest place of US, so it's a -9 degrees C.
Yeah.
But yeah, it's okay. It gets as cold as -60, so -9 is good.
Anything is relative only. So,
Okay.
with India, it is always, especially South India, it is always hot, hotter, hottest. So
Yes.
we just came out of the hot season, that is December. Rather, I'd say this year it was little cool because we had to use a little bit of what do you call a rug, a rosai or something little bit
I
in
see.
Hyderabad. It's not much, only 2-3 days we had because of some depression in north of, I mean in the
I see.
Bengal.
I see. Yeah, this place is basically, this is the only place I lived in my life that nighttime temperature could be warmer than daytime. It all depends that how cold air, what type of air, hot or cold, and where it is coming from. So if it's coming from north in night, sorry, south in night, then it is warmer. And cold air from north coming in daytime, it is colder. So it's all air wind pattern and the direction, wind pattern and actually the how cold or warm wind is.
Okay. So I did my experience in VHL R&D for about 36 years in power electronics and drives.
Great.
And then developed India's first electric vehicle.
Great. Congratulations. Yeah, that's great.
VHL sold about 1,000 numbers. Subsequently, because of profitability, we discontinued in 2006, and I made.
Yeah. So the reason I ask because Rakesh Chokhani is good friend of mine, and he's heading BHEL, Visakhapatnam actually. That's why I ask. Yeah.
Oh, I see. I'm from corporate R&D Hyderabad, but we are having a good interaction with the BHL Electronics Division Bangalore, and then Transportation Division in Jhansi, Delhi, Bhopal.
I see.
Just to keep us spending some time in introducing each other. That's what I'm saying. Otherwise, we are getting silent. So let us keep engaged some small talk. You are from India?
I am actually. I'm from a town, between Allahabad and Kanpur. Prayagraj. No, they named the city name Prayagraj, I think. Prayag. Like Allahabad, right? Old Allahabad and Kanpur. There's a place called Fatehpur. I'm from there.
Oh, Fatehpur.
Yeah. It's not Fatehpur Sikri.
Yeah, I always prefer that.
Fatehpur is a district actually, so it has been in being almost 1800 or some. Yeah, I'm from there.
Sandeep garu, please get the contact of the head of BEL at Vizag so that we will have a talk from him or something like that from him to benefit for our members.
Okay, sir, sure.
Correct.
Sir, you are telling about BEL means BEL or BHEL?
BHEL, BEL, not BEL.
Okay, then BHEL Vizag is basically a high pressure equipment plant, boiler equipment plant like thing. It's more mechanical.
Yeah.
Okay.
Yeah.
Products are more mechanical. Earlier it was Bharat heavy plates and vessels that was taken over by BHCL.
I see.
Because of government's policies amalgamating things. So they are more into the boilers and industrial boilers and other things.
Mm-hmm.
But good. That is good for our mechanical students also. Mechanical.
Yes, it is very good for mechanical.
Actually,
Yeah, safety, and particularly in the safety of boiler technology, this we can really see.
Yes.
Particularly the safety things are very, the norms are very, very interesting. If I read in Singapore, Australia, because my works as a safety of senior safety vice president cadre at one company at Singapore, he will be mentioning me many things about these things over telephone. Therefore, we can listen from him on that.
Yes, yes, it's very good. In fact, up to 2000, around 2013 or 2010 or so, one of my friends was a senior person there, like general manager level.
Yeah. So Rakesh Chokhani is overall head of that place, and I and him talk very often, and he want to enter into water. So how to purify water for various regions, irrigation, drinking water, and things like that.
In fact, BHL has got a vertical, what they call as water treatment business for power plants and other places.
Correct.
It's a very good business.
Yep.
Treatment, when I was in service, I retired in 2013. That time they were thinking that yes, sir. Very good area.
Sandeep, let us start.
Yeah, we'll start, sir. So with your kind permission, we'll start. Yeah.
Go ahead, Sandeep Gar. Go ahead.
Yeah. Good evening to all. Respected chair, IEEE Vizag Bay section, Dr. Lakshmi Narayan Garu, and today's program chief guest and IEEE PELS distinguished lecturer 2021-22, Dr. Brij N Singh, and guest of honor Dr. Rajagopal, Chair IEEE PES IAS PELS Joint Chapter Hyderabad section, and my dear participants, belongs to various knowledge groups, professional members, student members, non-members, faculty members. Very good evening to all of you. First of all, on behalf of IEEE PELS IAS PES Joint Chapter Vizag Bay section, so I thank IEEE Power Electronics headquarters for giving the approval of this distinguished lecture today. Also, we have planned to inaugurate NIT Andhra Pradesh IEEE Power Electronics Student Branch Chapter by our distinguished speaker in this program, as he is the right person to do this task. And this is our first event in this 2021, sir. And it gives me pleasure to give a brief summary of our chapter initiatives activities in 2020. So in 2020, actually we started a couple of events in the month of September, where we have inaugurated this chapter by Professor S.S. Murthy, a life fellow IEEE, and we have organized 16 expert lectures and 4 distinguished lectures by IAS CMD as a co-host, and then 3 administrative meetings, and then 1 awareness program and membership drive, and training programs on new student branch chapters are 2 we conducted, and successfully we have signed the petitions also, and this is also one outcome of one of this program. And online quiz programs also we conducted based on the IEEE standards specially, and IEEE awareness and all. And we also conduct one quiz program on remembrance of the Faraday's birth anniversary, and one skill development program also we conducted, and one program we supported for this faculty development program. And we try to tap all the variable like various possible resources like from industry and experts equally we balanced in 2020, and we arranged 4 talks by IEEE fellows, and you can see that 10 talks already delivered by the foreign countries speakers who are there already. And also we never compromise the arranging the qualities, with the qualified resource person. And we attracted the good number of participants, like more than 1,000 participants we attracted for these events actually. So successfully we have filed events, 33 events we have filed in IEEE V2 this year, 2020, last year 2020. So for this actually I thank the section Exicom and chapter Exicom and professional and student members, faculty members, and of course non-members also. They have very keen to participate, and then some of them they took the IEEE membership also. They encouraged us a lot, and also they participated all the events, and then they made all our events as a grand success. Okay. So with this brief introduction, now we'll proceed to today's program. So today we have planned the inauguration of NIT National Institute of Technology, Andhra Pradesh, IEEE Power Electronics Student Branch Chapter inauguration, and followed by the IEEE Power Electronics Distinguished Lecturer by Dr. Brij N Singh today. And I'm sure the participants will gain the knowledge and get benefit from this program. So thank you all. Now I request Dr. Lakshmi Narayana, Chair, Vizag Based Section, to give his presidential remarks.
Thank you, Dr. Sandeep and Professor Singh and Dr. Rajagopal. Rajagopal is a good friend of me for the last 7 to 8 years. We worked together at Hyderabad section in various levels. And that is one of the reasons I requested him to be with us today, so that he will bless us, our team and PES, PELS and IAS team, and suggest, because we are a young team, sir, Singh sir. We basically started our section in last, I think July is our last welcome letter came, July 27th. You might have seen that how good we did it in our section and chapter activities, and we got the best praise and highest financial reward from R10 also on the small section category. I congratulate Sandeep. He also got a outstanding volunteer for this thing from India Council Delhi also, for the continuing of the comprising of the 12 sections in India. Therefore, our volunteers are excellent. Honestly speaking, I just to do a clerical job of doing all the people's help. That's it. I don't do anything except helping them and talking to them. That's it. That rest of the work is done by volunteers only. But unfortunately, I am poking them to do the programs every day. Every morning I do that. Professor Singh sir, I need basically your blessings for our chapter section also. Kindly help us in future, that we would like to conduct an international conference with you in the level of PES, PELS and IAS or any other society, chapter, etc. in Vizag. We are a small team, sir. We are not a big team. Our membership is less than 500, but we already conducted 2 international conferences in Vizag. This year also we are conducting our conference, and our team is very excellent. I'm very happy on that part, sir. Thank you very much for giving this opportunity. I hope that our section, with the blessings of Dr. Singh and Dr. Rajagopal, will certainly raise more and get more laurels in future also, sir. Thank you very much.
So thank you for your kind words, sir. Thank you. Now I request Mr. Ramakrishna, the chair of NIT AP IEEE PES Student Branch Chapter, to give the brief introduction about our chief guest today.
Okay, thank you, sir. It gives me an immense pleasure to introduce our today's chief guest, Dr. Brij N Singh, sir. Dr. Brij N Singh is a technical fellow for electronics engineering in John Deere, USA. He received BE from M Technical University, Gorakhpur, ME from IIT Roorkee, and PhD from IIT Delhi, all in the domain of electrical engineering. In 1996, Dr. Singh joined the ETS Quebec, Montreal as a postdoctoral fellow. In 1999, he joined the Concordia University, Montreal as a research fellow. In 2000, he joined the Department of Electrical Engineering and Computer Science, Tulane University, New Orleans as an assistant professor. In 2007, Dr. Singh has joined John Deere USA as a power electronics staff engineer, where presently he holds the position of Region 4 Manager External Relationships. Dr. Singh has published over 90 research papers, and he has 28 approved US patents, 1 trade secret, and over a dozen pending patents. In Tulane and in John Deere, Dr. Singh has won numerous awards. He is the winner of 2020 IEEE Power Electronics Emerging Technology Award. He is a senior member of IEEE and recently has been selected to serve as a IEEE PELS Distinguished Lecturer for year 2021 to 2022. He lives with his family in West Fargo, North Dakota, USA. Thank you, sir. And over to Sandeep, sir.
Yeah. So thanks for introduction. So thank you very much, sir, actually, and we are honored to have you today. So thank you so much, sir. Now I request you now, Dr. Singh, to inaugurate the NIT AP IEEE PELS Student Branch Chapter.
So let me share my desktop, and you could hear me, right?
Yes, yes, sir.
Okay, and I have this headset on, so let me see if it comes out, right? Otherwise I can do again. If you don't hear sound, let me know.
No issue, sir. Yeah, thank you, sir.
Welcome. So I will share my other desktop as a PELS deal. I am obligated to do some marketing promotion, which is fine. But before I go, a couple of remarks on Dr. Lakshmi Narayan and others here, Dr. Rajgopal. I will be really honored to help whatever manner I could, and I will certainly pull in some additional deal from other society and powertrain society to basically share their thoughts and knowledge to increase know-how at your place. And certainly I greatly appreciate that you feel like so humble that you are just merely serving like a clerk and enabling younger generation people, new leaders, empowering them and allowing them to take decision and all that. That's really great, because this incumbent upon people like us to produce future leaders. So I greatly appreciate your humbleness, your down to earth attitude, and enabling new people, younger generation. So that's great. I glad to hear that. So I'll just start drilling into, and please ask question in midst of my sharing this slide. So you could hear and you could see it, right?
Yes, we are able to hear you.
Okay.
And see your slides.
Great. So this is basically, here we are talking about powertrain society and what it does. Essentially, the society was founded in, and I plan on not reading into text. That's not me. I like minimum text in my slide. But 87, the society was founded, and now it has over 10,000 members worldwide. And these are the officers. So Lui Chin Chang, I met him in numerous conferences and all that. Very nice gentleman. I think, if I'm correct, he is in Canada. And Freddie, everybody knows Freddie travels India quite a bit. He has been in Delhi, and in fact, I was in Jamia Millia Islamia, and Freddie was there. I saw his picture in one of the poster, and then I also went to give a lecture there. So people know him in various schools in India. And Alan is in Arkansas State University, good friend of mine. So pretty good, connection here. And then these are the PELS AdCom officers. Pat is very popular in conference. I met him many times. He's in UK, and John is, we call him Owen. Actually, he's also a good friend of mine. And Brad is somewhere in Boston area. And so I met these three guys. They know me in person. And then these three people, I have seen them in conferences and all that. So if and when any help needed from these people, I can certainly help out. So so what is the membership benefit? You could get the print, electronic, digital subscription of, IEEE magazine, 1 year free, 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 Online subscriptions are possible in various and Sandeep, you have this slide, so you can share with the people there, including a student. And then IEEE Powertronics also launch open access journal, so you could publish your research there. Then other benefits are you could go attend conferences, attend workshop, and I'm involved actually one of the workshop called as BIPDA, which is wide bandgap power devices and application, and pretty like it's like a conference, but they call it workshop because it focus only very specific type power devices and their application. Then your resource center, oftentimes it's a free for PELS member. Then you could be involved in various technical committees if you are member or you are a student member. And the networking opportunity to go to attend these conferences. I do attend every year APEC, which is Applied Power Electronics Conference and Exposition. I also go often, actually 1 year I skipped since 2009, ECCE, which is Energy Conversion Conference and Exposition. And it happens in actually 3 regions of the world. So North America was the one I attended, and ISPEC and COMPEL and PEDG. So these are some of the content that IEEE Powertronics is involved in. You could participate in these activity, technical committees, conference committees, chapters like yours. Women's in engineering is big push, so girls student could be early on get involved in leadership role, volunteer role in this activity, and then mentorship events happen during conferences. And these are a couple of some highlights, pictures. So distinguished lecturer program, I don't know when it started, but in 2020, 2021, these are the members. And actually I know Helen, she's in Florida State, and she's the one actually encouraged me to become PELS DL. And so these guys can be requested to share their thoughts, and only one is from industry, but most of them are from university. And this year, I think they recruited 4 new people, including myself. And apparently, I know only Smedley. So, but you guys can request, and every one of them have their bio and picture in the PELS website. So you could just look at what they could offer, including even the lectures that they could. And then PELS Broad Student Program, IEEE Future Energy Challenge, Student Travel Grant. So if you are attending some PELS sponsored conferences, you can apply and you probably will be approved. Mentorship program that happens usually on-site these conferences. It's like hour or 2 long sessions, senior professionals advising students and early career people. And then there's another program. I have been actually in this one, and there were a couple of people from India did receive this recognition, which is basically if you submit your PhD thesis, title and all that, and there's certainly requirement what you need to do. But if you get approved, then you go on a stage in front of 200-300 people and talk about what you did in your PhD. And then standard are there being developed. So one is involved into the standard, and then there are these guys in the hill and things like that. And then IEEE Powertronics is home for transportation electrification community. And I did give one tech actually webinar last year, and that was attended by roughly about 500 people. So it's pretty good from visibility wise, and they're supporting it. And then so encourage you to join PELS today, and it comes with benefit that if you join, particularly students are joining, they would get 50% discount. I do remember when I joined IEEE in 93 or so, I did enjoy this discount for a couple of years, and then I graduated, then I became full member. So when you go and check out your membership renewal or an enrollment, you need to dial in these codes, and then you would automatically your bill reduce by 50%. So this 50% discount is applicable to IEEE as well as PELS both. And then these are basically the what you call administrative officer for this society. And I know Alicia actually very well. She was the one who roped me and do that tech webinar a couple of years ago. And that's about the advertisement piece of it. But this is, I can certainly share this slide, and you could benefit from there. So how about this slide? It is coming.
Yes, we are able to see your slide and hear you also.
Okay, I'll put in presentation mode. So this is my talk, and let's see if I can minimize some of this here, but if not, okay, yeah, it's gone. So I will basically be talking about improved control algorithm for power quality control converters. And if you read a couple of research paper I wrote, then you would be able to develop the hardware by yourself. And a good power trans engineer is that can have hands-on experience, hands-on things, like really can make and break and fix things. So outline of my presentation would be a little bit about myself. Already I was introduced, but talk about, my mainly what I did over the year. Three-phase control power converter, three-phase and control power converter, I'll touch upon that. Then I will talk about power quality issue and solutions, mitigation methods, few highly cited control algorithm for power quality control converter, because it's a very rich topic. So I just want to give a little bit disclaimer there. And then understanding real and reactive power, various control methods of voltage source inverter, which works like an active filter, novel indirect control algorithm, which I was involved instrumental developing, performance comparison of various control methods, studied dynamics, operation of this and some results, and few implemented what we call power balance theory. There are numerous theory, but power balance theory we worked on three-phase, three-wire system. And then now new devices are emerging, which is wide band gap devices, silicon carbide, gallium nitride. So how they can impact, these devices could impact control as well as power converter construction and cost, size, and things like that, followed by conclusion. So I was brought up in India, and all my degrees are from India, and this is my over a year experience. And currently I'm a region 4 manager external relationship in John Deere. What that entails is I have to go out and work with university, work with non-compete industry and government entity to get the grants for new research projects in various areas, not only in power trans, but many other areas that John Deere is involved in. And then region 4 actually goes US, Canada, Australia, and New Zealand. But mostly we would first do, and this is newly created position, never existed before. So I need to do a lot of learning, but mainly North America, then followed by Australia, New Zealand. So it's like a global type role I have to play. So three-phase uncontrolled power converter. So this is one of them. So you may have a diode rectifier, and then you may have a three-phase source between rectifier and load here on the far right, and the source on the far left could be tied with the source impedance, which is basically inductance and resistance, and that does some trick, And then another load could be diode rectifier RC converter, and these are infested with the harmonics. And if that is the case, then what you do about it? So so this is actually called as a point of common coupling. Means here not only your load would be connected. So think about like this is industrial load. You can think about this is one industry, one big company having a lot of loads there, and there could be another one here, another one here. So everybody is getting power feed from here, and if one of them is corrupting power quality at the power point of common coupling, then that's a problem. And problem is like if somebody else has a power factor compensation method, most of the harmonic will flow there. And then his or her electricity will go up, so that's not desirable situation. So the idea is that IEEE came up with the standard called IEEE 519 standard. As per that, you must be compliant with certain amount of harmonics in voltage and current at PCC. So if you connect your load, you have to be responsible for your load if it is generating harmonics. And same thing in the RC load. So in the RL fed load, harmonic is roughly 30 to 34%. It can produce distortion in the voltage. And in the RC load, it is even current is in peak in nature, so it gives even higher than that, 50%. So those loads are called nonlinear load. Means if the waveform shape changes with the load, as you vary this load and voltage waveform shape changes at this point PCC, then you are generating harmonic and you are non-linear load. So no longer sinusoidal, non-compliant with IEEE 519 standard. So what you do about it, what it does basically, so THD is measured in the voltage and TD is measured in the supply current. So both are measured harmonic, but harmonic in the voltage is called a THD, total harmonic distortion, and harmonic in the current produced by your load is called as a TDD, total demand distortion. As your demand, like load demand, which is reflected by current, is varying, then you would have variable TDD, right? And these are two power quality issue, and there are numerous other, like a voltage flicker, voltage fluctuation, and then brown out, blackout, single phasing, and voltage unbalance, and all those kind of stuff. Voltage in current in rush, those are additional issue, but TDD, THD and TDD are usually most important power quality issue that load can introduce. So why it happens so imagine that if you have RL load, then current waveform will look like this step wave, and it may not be that obvious on your end, but usually it generates the kink. What that means is whenever current is suddenly changing, and the nature is because there's a commutation of diode pair, right? So until this one diode pair was conducting, and as soon as this point comes in the waveform, depending on forward reverse bias of the diode, then this load kicks in, this pair of diode kicks in, right? And then current becomes like this. So due to commutation, phasing in and phasing out diode pair, you see this type of current, and that sudden rise in the current produces little bit kink in the voltage, and as this current gets higher and higher, more distortion happens. And imagine that if it's a thyristor type load, then even that generates even far more, because commutation of thyristor is really very fast. It's very hard switching device. And then in RC load, actually it is even more obvious, because RC load has this type of current. So you see how voltage got distorted right here versus this. Like this is a load, this is the source voltage here, this top waveform, and this is current that is here, and this is source voltage at PCC, which is not desirable situation. So what you do about it, right? So you could, what is missing here is that load doesn't demand this difference of the current. Like imagine that if it was a plain simple linear load, means no diode were involved, then our current would be like this, right? But then since you introduce diode, because you want to rectify the voltage waveform, you want to turn AC into DC, and if you did that, then your load current will look like this, and this is what is missing, right? So you have to be careful. So what that means is you are responsible of producing this signal, which is unwanted, undesired. And in RC load, even it is far more severe versus RL load. So what that means is you have to design a controller that can vary automatically, seamlessly varies bandwidth, and then compensate the harmonic. Like see, there's a sudden change in the current here, right? As similarly here, RC is far more pronounced versus RL load. So you need to design control bandwidth of current control voltage source inverter, which is active filter, plays a vital role in compensation of current harmonics. So that's what actually I'm trying to drill down now. So what you do, you have a diode rectifier load. In parallel, you connect another source, which is going to compensate that harmonics. So this is current control voltage source inverter, called works like active filter, and that's what is going to make the current sinusoidal. The current basically source here must see current and voltage sinusoidal. So what is the active filter job? It compensates harmonic, it compensates reactive power. So any load that when the voltage waveform is not sinusoidal, at the PCC usually has reactive power in it, so total demand distortion, total harmonic distortion. So if current and voltage are not in phase because of distortion in the current waveform, then it has some reactive power. So this also supply reactive power. And then control bandwidth of AF can be dynamically controlled using feedback method. So you have to basically apply the feedback and feed forward method to do it. So so-called indirect current control method. So feedback method and feed forward method, I'll talk a little bit about that as I go more in about it. So these are highly cited publications. So years ago in 84, Professor Hirofama Akagi, who is from Japan, wrote this paper on the power quality converter, and it has received to date, 2 days ago, actually, as many as 4,500 citations. And we began working on the power quality when I got into Montreal, and prior to that, Professor Bhim Singh from IIT Delhi, he was my PhD. It was very thorough gentleman, and very well known in India. So he was in Montreal, and he was instrumental getting me there. Actually, he said that these guys are not working on any experimentation. Why don't you go and start something like that? So anyway, so we started working on this at that point, experimentation. So we wrote a research paper, and this also receives quite a bit number of citation. And in fact, from this group actually, that I would include myself, this could be probably one of the highly cited research paper, means a lot of people referring it. Improved control algorithm, which I further took it and wrote this one called a indirect control method. And then, this also have quite a bit citation. And then 3-phase 4-wire system based paper I wrote, was involved into writing and developing experimentation and all that stuff, is also quite a bit cited paper. So what I want to disclaimer here, that there are over 1,000 research paper published, and it is beyond my ability to review them all, identify their uniqueness and research gaps. So I don't claim that all these 4 paper address everything out there. It just want to make sure that I don't want to convey a wrong message here. So content of this slide is based on slide deck is based on mainly these 4 papers. So let's drill down into understanding real and reactive power and reference command, how you could generate for this current control voltage source inverter. So there's a Clark transformation, Park transformation, you guys know. So ABC, plane ABC frame waveform voltage current can be transformed into alpha beta frame by very simple equation, no angle, nothing involved, no trigonometry is involved. This is a plain simple math. And same thing you can do for the current also. So alpha beta quantity can be transformed into they can be used to calculate real and reactive power. So essentially, once you have ABC to alpha beta, so B alpha, B beta quantity, you can multiply voltage and current in B alpha, B beta, sorry, B alpha and I alpha. Then you get what you call the No, I'm sorry. This is a 3-phase. Actually, this is instantaneous power calculation. So all 3 quantity, voltage and current multiplied by this, you could get actually real power. So these are matrix form these, but then same real power can be used by using the alpha beta quantity, right? So B alpha, I alpha multiplied together, added them together, you could get same power that you have gotten, B alpha, I alpha, sorry, VLA, ILA, VLV, ILV, and VLC, ILC, added them together. You can get same value using this. And then reactive power can be cross product. So dot product, cross product. When you put in the matrix form, it will look like this. So dot and cross product of alpha quantity provide real reactive power consumed by load. Quantity Q doesn't represent power due to orthogonality between B and I. And what I'm trying to say that if you take the basically this quantity and see the angle between this and this, and are this quantity this, then you will find that it is more than the 90 degree, right? So that's not, they call it as a orthogonality issue. So then you cannot call it as a real reactive power. They call basically it doesn't represent the reactive power the way we know actually. So that's what they're trying to say. And Akagi actually did quite a bit work on this. So so then the negative sign is because of the angle is more than 90 degrees. So to represent it, you basically have the negative sign. That's how you could basically begin to call this as a Q. So now what is the compensation? Basically, if there is a nonlinear load, the power consumed by this load can be split into 4 componentry. So real power can be split into real DC power, real time varying power, and reactive power by load can be split into DC reactive power and time varying reactive power. And ideally speaking, if this was only RL, only R load or even RL load, actually R load, only R load, like a three-phase source, and only you have a resistive load, then the source would be responsible to only supply DC component of real power, nothing else. Rest of the things should come from somewhere else. So what that means is, if you want this system to behave that at this point here, source should see rest of the things. This could be like industry, like a locality, like colony or whatever. If this transformer feeder here, imagine there's a transformer feed, if that want to see that I am seeing only resistive load, everybody just have a resistance connected in their houses or their building across the power line, then the supply system will supply only the real power, DC component of real power. But the problem is that that's not the case. So how you turn that into behaving like this? And that's exactly sinusoidal system is designed, transformer, all the power component are designed to really operate for sinusoidal with the sinusoidal type system, right? But that's not the word. Word is basically goes for non-linear load, right? A lot of rectification and a lot of pulsating loads are connected. So if you want to do that, you have to connect a control converter, and then this converter will supply rest of the power, right? So it will pick up P tilde, Q bar, and Q tilde, which is basically the time varying real power, and the time DC reactive power and time varying reactive power. So you need to pick up these 3 quantity by this. And if you did that, then at this point, this converter will behave, the load will behave like, hey, I am just seeing only resistive load connected across the power line. So distinct function of power quality control converter is actually to supply only, make sure that supply only supplies the DC component of real power and nothing else. So definition and physical meaning of instantaneous real power. So you have seen this equation before. So what you could do, basically you calculate the power using instantaneous method, and then you could take that matrix that I had earlier, right? You can take the alpha beta quantity and have these power, and then you can start getting the I alpha and I beta. And why I have this star, because now I'm going towards getting reference quantity, because I want to put this current control converter into a control mode. And to control any system, you have to have a reference and you have to have where your target, right? Feedback system. So reference and actual quantity are put together in the controller, and then controller is the one that is forcing it to behave like a current control voltage source inverter. So then you can split this into further. So this component is because of the real, this component is because of the reactive. Then further, exploration of that happens. And then you could basically I alpha, I beta component T could be, these are the reference current due to real power, reference current due to reactive power. So alpha beta current due to real power, alpha beta frame current due to reactive power. So bear with me, I'm trying to get into what are the quantity I need to control this converter, right? That's what I'm trying to do here. So there's a lot of math here, and repeat a little bit, but then further this matrix simplified. So now I have alpha component of real due to real power will be look like this. Then beta component of real power look like this. Same thing, reactive power. And then further simplification of that matrix. Right. So I now gotten these quantity and then put further into matrix form. Then finally, my reference reactive real power will look like this. So further simplify, this is just manipulation of these matrix. So my equation will look like this. And then I would put that, real power that will look like this. And then this is actually the reactive power. So they say 0. The sum of instantaneous real power PP alpha and PP beta coincide with instantaneous real power in the three-phase load circuit. Therefore, these are named as instantaneous real power. But the sum of instantaneous power PQ alpha and PQ beta cancel each other and make no contribution to instantaneous power flow from source to load. Therefore, sum of PQ alpha, PQ beta are called instantaneous reactive power of the load. The instantaneous reactive power must be compensated to make sure load behaves as unity power factor. So then the real power again decompose into two pieces, reactive power also into two pieces. So then my further manipulation, and by the way, that is all this derivation is given very detailed in that research paper I wrote. So if somebody want to go further read and follow, because it's a lot of math here. So I alpha is expressed into 4 components here. And I beta, IL beta is expressed into 4 components. So now I have gotten my alpha beta reference quantity, load reference current into 4 component, and now I can basically, so this is a little bit recapping, all the math, right? So this is alpha, this is beta. So what I could do now, that if I want to control this converter, then I will basically take those IC alpha and IC beta component. These are actually so what are these actually? Which one I can call IC alpha, IC beta? So think about that. I told you earlier, right? This supply system is responsible to only this part, right? and then rest of the things P tilde, Q bar, Q tilde should come from this converter. So what that means is if I want to have my reference current for this converter, I just drop this component, and I would get my reference quantity, reference current quantity in alpha beta frame for this converter, this current control voltage source converter. And that's exactly I did, and it is in diagram form like this. So from them alpha beta, I do inverse spark transformation, and then I get three-phase quantity ICLA, ICB, ICC, and these are star, right? So these are my reference quantity. Once I get reference quantity and I am sensing actual quantity, then I put this current control converter into current control mode, and then this would begin to start supplying these three part here, right? So only compensate. Let me see why I'm saying so. Okay, yeah, actually what I'm doing is here. Let me go back here. I'm basically compensating only these last two parts, actually this one and this one. That's why I call it. So this one right now, I'm only compensating reactive power like a DC and the time varying. So if I want to do, this one has a 4 component, right? And now I can choose because I know all these 4 components, right? So my controller will know that what are these 4 components independent of each other, and then it is up to me that which one I want to use. So if I use only last 2 component, only the reactive power related, then I would only compensator will compensate only reactive power. That's what it is actually. So then the IC alpha, IC beta here that you get is calculated by math here, implemented by this block diagram. And then I would say ICA, ICB, ICC is based upon these. So a fraction of load current could be supplied by current control voltage source inverter. Right, so that has some problems. So if I want to do a little bit more, I want to pick up the P tilde as well. And that's why we modified this control method. So basically to go back a little bit, so this is what Akagi did actually. When he developed that theory and that paper, that is a highly cited paper, this is exactly he did. So then we said, no, actually, we need to compensate even this component as well. And that's why we picked up this. So that's what we call it is modified direct current control method. And why I said direct, because I'm controlling this converter, this current control source converter, and I'm using the control and reference and actual quantity of this converter. That's why I call it direct control method. And later on, we did what you call indirect control method, where we were using actual and reference quantity here. Controlling this converter but using quantity here. That's why we call it indirect control method, and we found significant improvement. So what I did minor modification. I just extracted P tilde from the P and then added that, and then that's how my reference quantity became. And actually what I'm trying to do, Akagi had this component, I added this one in addition and then got reference quantity. That's what I'm doing. So then I compensate these component and ABCD command are then realized from these, right? IC alpha, IC beta to ICA, ICB, ICC. So a larger fraction of current is supplied by controller. And then basically you implement that into DSP. So what you need is actually 3-phase load current, 3-phase load voltages, voltage at the input of that converter and non-control converter. And then rest of the things happens in DSP. You are not sensing any DC voltage and all things like that. And then you get the response like this. So what that means is as soon as you turn the controller on, you start turning this supply current that were like this, load current, supply current were same, right? But when compensator it turn on, then supply current begin to start shaping them sinusoidal. The problem is that you see these notches here. This is because of the feed forward method. This method is actually feed forward method. So it doesn't know what is happening in the supply. So it doesn't have any information that supply current have notches, and because of that there's a THD in the source current. So what basically we did, we want to get rid of those notches, and that's where this what you call modified novel indirect current control method came. So we did basically P componentry, right? But we are still forcing the controller to supply the what you call reactive, like a time varying component of the real power. That's why only this quantity is used. So you get reference current here, and then controller is controlling, controller is control based by quantity here actually. So that's called indirect control method. And then once we did that, then those notches disappeared because now it is a feedback method. So controller knows that when there's a current is transitioning, then the notches, and I want to compensate those, right? So those are gone. But the problem is that my reference current is distorted, and the reason it is distorted because I still have a P tilde component coming from the supply. I'm only the Q bar and Q tilde are being supplied by active filter, and P bar and P tilde are coming from power supply. That's why you have this this distortion in the reference current. And if you have distortion in reference current, then you can't do anything. Controller is going to basically follow the reference command that you are giving it. So what we did, we basically said force the controller to only provide, force it that supply system is now only providing the real power of DC component of real power, right? So I added a filter here. And then once that I did that, then that did the magic. So now I'm basically supplying only four. You remember that I had a 4 component of load current, right? So I now only doing one of them, the first one, and supply is only responsible for doing the first component. Once I did that, then I brought back that diagram earlier, right? So only real power is being, DC component of real power is being supplied by the supply, and rest of the component is coming from the controller. So once I did that, then you see that reference current is better now because I am shaping it. I'm now eliminated that P tilde component, and once reference current is better, then of course the converter is going to follow, the controller is going to follow the reference current command. And then this is the how it should be. Means what I'm trying to say, that the supply is only responsible to supply the real power, DC component of real power. What that means is, if you have a supply system and you have a lot of garbage, lot of load here, but if you begin to compensate all that, then supply should see that only resistance is connected across the power line, nothing else. No inductor, no capacitor, no diode, no switching elements. So that's exactly it should be. So if you use this method, then your supply system will see, okay, I only have resistance connected out as a load, and the utility company, power company, transformer, transmission line system, all that will love it because they are designed for this kind of, they are not designed to operate for non-central system. So basically now I'm comparing these 3 methods, right? So this method was basically, I modified that Akagi method and I ran into this notches in the supply current. Then I did indirect current control method, means that I'm only supplying Q tilde and Q bar from converter. But once I start supplying P tilde also from the converter, then I have far better power quality waveform versus this. So that was the improvement we did in that paper that is very highly cited. And still people to date, use it. And these are 3, what you call the comparison. So, all three methods. So your load THD would be 29%, assert TDD would be 29%. With one method, you have gotten 10.2. You need to go below 5. With the other method, because distortion, you have 7.1. And the last method, which is super improved method, you have 3.2. So it works on a feedback method. These two are feed forward method. So because of feed forward nature, you don't have this information. With feedback method, you have this information. That's how I explain it. Actually, usually you are compensating out of 4 component, you are compensating 3 of them. Out of 4 component, you are compensating 2 of them, and here also 2 of them. But this is feedback method, this is feedback method, this is feed forward method. So that's how I took it. So then you basically suddenly switch, like it's, switch response. So voltage for page A, but the current page A, B, C. And once you did that, so this is a steady state operation. And in university, you can't go very high power. So we were roughly playing about 500 watt to 2 kilowatt range. And then when you change the load seamlessly, load is changed with no problem, and then the current remains in phase with the voltage. So this is the setup actually I hand developed in when I was in ETS Montreal, and my setup it's all made by me. And even today, when I go there once in a while, program Rich Chandra, some of you know him. He is Bhim Singh classmate, from IT Delhi, IT Roorkee. He had this, he treasured this hardware actually, and he always jokes with me, Brij, चलो चलते हैं कन्वर्टर को चला के देखते हैं, right? So what I'm saying, it is a hardware that I can, if I give a day, I would let it go. It will function. So it's I know all the details, and it were 2 converter. I did a lot of power quality work during that time in 2.5 year duration, a lot of work, and that resulted in over 40 plus publication, my work there in 2 years. So this is my picture in Montreal in front of my setup. So most used topology is basically that this you could basically reduce the third, you can eliminate the third page and put the sorry this we are talking about 3-phase 3-4 wire system now. So I'll skip a couple of slides because of time constraint. So this 3-phase 3 wire system, and this is 3-phase 4 wire system, and the reason is that when you have unbalanced load, oftentimes neutral has a lot of current, so you want to compensate that. That's why 3-phase 4 wire system are very commonly used hardware. So I will talk about a little bit power balance theory. So basically what you could have a diode rectifier, you could have a 3-phase 3-wire system or 3-phase 4-wire system. If you have a switch here, you just turn it off, then it will behave like a 3-phase 3-wire system. If you turn back on, then it will behave like 3-phase 4-wire system. But you may not have a luxury of having the load like this. You may have a 3-phase load, but all 3-phase load are single phase, one like a plain, single phase diode rectifier RL load, single phase diode rectifier RC load, but little bit linear load, and then single phase diode rectifier fed RC load. So you could have a mix of these load. Imagine this is a colony, right? Somebody has a refrigerator, somebody has a lot of nonlinear load, our industry even, like somebody doing building operation and things like that. If you have those kind of load, somebody may have arc furnace. If they have this, then the supply system will see, oh, what is these guys are doing, all of them together. The supply system will see that these guys are doing something like this. Some people have a 3-phase load, some people have single phase, linear, non-linear load. Somebody has a mix of linear and non-linear combination, things like that. If you did that, you can put a converter like this and you can compensate the harmonics and reactive power and balancing, and load also may not be balanced actually. So you need to, even this system can balance the load. Means at this point, the supply system will see rest of the things, anything from right from here, we'll see 3-phase balanced sinusoidal system. That's what you will see if you do proper control, proper design, and all that. And by the way, this paper I wrote, and there's a lot of detail. If somebody reads this paper and try following the hardware, even I give the tip that how you design the hardware, a lot of analog design, digital design, and you would be able to basically design the converter. I was able to design this design and put into practice within 2 months. So if a student want to follow it and want to do a little bit hardware work, related, which is hands-on experience, they can indeed flip that paper through and they could do it. So in the power balance theory, what it is basically, I sense 3-phase current, 3-phase load, and then I get one component of current. But power balance theory method of active filter does require that I must sense the DC bus voltage of active filter, and then I do energy balance. If I did not do that, then DC bus of active filter can collapse, and I'm no longer able to compensate the harmonics and reactive power and all that. So this is a different theory called power balance theory. It's a very detailed explained in that research paper. And then this is power balance theory, which like a what do you call the 4th phase, so 3-phase 4-wire, and 4th wire is basically simulated using center type capacitor like this. So I have a 3-phase converter here, but 4th phase is like this. Rest of the things is same as here. So as soon as you turn on the converter, you get, what do you call the, and by the way, this is indirect control method. So I am basically controlling the, actually, there's let me see. Yeah, I think there's some mistake here, because otherwise I should have gotten notches. This is actually that indirect control method. But anyway, so when the converter turn on, then you see sinusoidal current and logged in phase with the voltage. And then I must be careful that voltage across both capacitors should be equal, right? And then I see that the only switching notches are because of the switching behavior. And then if this neutral point is closed, then you see the current flowing that neutral conductor as well. So if load was unbalanced, then you would see a lot of current flowing here. So now I'm simulating. This was by simulation. I couldn't experiment it because by the time I was leaving the place. So 3-phase current, now 3-phase different type of load here. 1 phase is drawing current like this. 2nd phase is drawing, let's see, this one is current, yeah. No, actually this is 3-phase identical load. This is 3-phase, basically all phases have RL load. So 3-phase, single phase RL load, and then as you turn on the compensator, then current becomes sinusoidal in phase with the voltage. And then once load is increased, then there's a decrease in the DC bus voltage because of the energy balance that earlier I was telling. Actually this piece, this part should be fast enough. You have to have very fast dynamic here, but DC bus recovers and it keep compensating the converter. This is a neutral current. No, actually I need to go back. Sorry. Yes. So neutral is closed, right? So, and here these are now 3 different load, right? So first phase is RL, second is RC, and linear, and third is actually plain RC. And if you have 3 different load, three single phase load, different type, and then converter will still able to compensate. So phase A will provide current like this, phase will provide current like this, phase C will provide this. Since it is a current control mode, right? So it will, power lines will force itself to behave like a source like this, and the neutral current will look like this. So what I'm trying to say is that if you put this into current control mode, it is going to provide what you need. And then high frequency. So what are the basically, now I'm almost end of my presentation here. So what are the wide bandgap devices application, how they will impact the power quality control converter? Basically high switching frequency, passive size can go down. So imagine that the inductor that I used, they were 5 millihenry type parts. And when we are doing hundreds of kilowatt converter, then each part can be very bulky, right? I did 1 kilowatt, but imagine that load in megawatt. And if you have megawatt type power converter, then these parts are very large. But if you go high switching frequency, then they become smaller, right? So that's what passive component size, like this capacitor, the inductor can go down in size, and then cost will go down. And then converter is actually wide bandgap devices are high efficiency devices, so they have less losses, turn on turn off losses, as well as conduction loss is less as compared to silicon IGBT. So then they would reduce cooling requirements, so overall converter size would be much smaller versus if you were using silicon devices. So silicon carbide gallium nitride devices can become a cost competitive solution to compensate quality of the waveform, current and voltage if you go high switching frequency. Power quality issue could be addressed at a higher voltage, like if you could do at a distribution level, but you can even begin to do 11 kV or 13 or whatever higher voltage level versus 480 or 110 or 220, depending upon which country you live in, right? In US it's a 220 or 110 single phase. In India, I think it's a higher 480 or so. So essentially, you can go even from distribution, you can go like a feeder level, like 11 kV, and those level you can start doing compensation. So that's what, and the converter would be medium voltage level. Since you can switch converter higher switching frequency, so bandwidth can be, controller bandwidth would be much faster, so you can respond faster. You saw that DC was voltage dip earlier. That can be even eliminated if you go high, because controller bandwidth is able to respond much faster rate. And where dynamic response can be needed, like a building operation, right? In building operation, operator is touching the, like whatever he trying to join to, let's say, two pieces of iron by building, then the arc current that flows in is highly dynamic nature. So in those places you want very highly dynamic power converter, and if you want to compensate that power quality because of coming from building, you probably wide bandgap devices could be much more useful versus silicon IGBT, silicon MOSFET. Then same thing, arc furnace can produce harmonics, and if are sudden reactive power demand and things like, because arc is actually an inductive nature. So if you want to compensate all that, probably you need wide bandgap devices. So I would then conclude power quality issue related to THD, TD covered in detail. Control theory of active filtered are covered mainly like a direct indirect control method. And I see questions are popping up, so I will address them as later. I should have engaged a little bit more interactive, but anyway. So theory, reactive power theory, instantaneous power theory, power balance theory were touched upon. Experimental setup was a little bit described. Particularly, I couldn't go much in detail because time constraint I have. But if you flip through those research papers that are given in presentation, you would get it. You could get more detail about this. Experimental results were discussed for various operating mode of the, like a various type of load, direct, indirect control method, sudden load change, start up with the converter and things like that. Balanced load, identical, non-identical, unbalanced load. And three-wire, four-wire system were talked, simulation results were also talked about. So that's I would be happy to answer question, and if you ever want to get in touch with me, this is my email address. Please do. I get a lot of emails, so please do mention that you were in this presentation and this is what your question is, and I would be happy to answer, including even mentoring or your guidance that you need from me, particularly students for your career advancement, what you want to do next. Any undergrad student want to come and do master PhD in a Western country or in India or whatever, I would be happy to even guide that. So let me see if I could basically get the questions.
First,
Go ahead.
yes, sir. Yeah. Thank you, sir. Thank you for a wonderful presentation. Now I request Dr. P.V. Rajagopal to share his views.
Should we
Hello?
answer some of the questions or should we?
Yeah, we will answer after this, sir.
Okay,
Yeah.
sure, please. Yeah, go ahead.
Dr. Rajagopal, sir. Yes, please.
Yes, sir. It was an excellent lecture by Dr. Brij N Singh. I would say it is a very quick and thorough coverage of active filters and their applications, especially the new method you developed. I could see it is very effective. And from the comparison you have showed, it was brought down to, I think, 3.42 or something around that, less than 5% respond. It's a very good feature. And these active filters are very much important today, more and more in the solar power area. From my experience and from the experience of my friends, they are saying that the Greening the Grid India policy, which is aimed at high penetration of renewable energy sources into the national grid. The planned penetration level is around 22%. It is giving 22% with the Government of India's plan of having 175 gigawatts by, I think, 2023 or so. So there was a study done by Ministry of Power and some US organization and others. They have worked out that with the such an installed capacity of 100 gigawatts of solar and 60 gigawatts of wind and 15 gigawatts of other sources, the penetration level of the renewables into utility grids around of 22%. These are creating a lot of problems, especially at the high voltage level integration. Like we know, we connect these high power solar power plants at the solar parks, which are in megawatt level at the 132 kilovolt or something higher, 220 kilovolt. So there, all these active filters are all very much important. In fact, I remember when we started the work in BHL corporate R&D, my colleague Dr. BP Muni was working actively on these things. So when around 2006 or even before, when these solar power plants were sold by us, when we developed it, the requirement was only for active control of the load. But more and more, the reactive power has also been built into the power conditioning unit operation in the solar power plants. And they wanted an independent Q and active power and reactive power control, just like our vector control methods and motor control. So with all these things, the vector control started getting implementation. And more, the power quality issues are becoming. In fact, one of my friends in the field, who is from AP State Electricity Board, he was asking one question that IEC, this IEEE 519 is a benchmark in many countries. Like even CE specifies that as a benchmark for the contractors to meet. And what he was telling is the percentage THD allowed is around 5% at the low voltage level of integration. Whereas when it goes to 220 kV and above, it is reduced to 2.5%. So I was asking why that stricter maintenance. We thought it is only because to limit the absolute value of the individual harmonic. I think that's what you can clarify in it why it is done. Second is now with the new standard coming up, IEEE 1547, I think, if I remember, the norms are getting further improved. I mean, further stringent. So maybe you can throw some light at the end after taking others' questions. I don't want to take their enthusiasm. So this is my knowledge of this area. So your presentation is very apt, relevant, and highly useful for the present day engineering requirements of Indian industry in the power systems especially. And the advent of wide bandgap devices, if we can take advantage and use them in these active filters applications and power systems, it will be a good thing. That's what I feel. And Indian academic side, they should work in practical implementation of these things. Just for your information, I would like to share with you that we developed in BHL R&D by Dr. B.P. Muni in 1990s, StatCom, D-StatCom 1 MBR type installed as a demonstration, technology demonstration project in Midhani Steel Plant in Hyderabad. It's a ferrous metal processing plant, a steel plant it is. Subsequently, we made a 3-level inverter based 2.5 MVR StatCom for furnace arc flicker controlling Belay steel plant. It was a DST funded 5 crore project. We implemented, it's working very well. That was done, I think, around 2012 or so, with the DSP control and all, with 3.3 kV IGBTs for 3-level inverter and all. NCD, that is neutral clamp device, a diode, I think, because I left the field for a long time back. Still, I am trying to recollect those things. So, what I'm trying to say, your lecture is highly informative, educative, and very, very innovative solutions you have brought. I hope the industry in India will use it. And the academic side, they should try to update this information to the industry and try to take some projects as a technology demonstration projects. As you have mentioned, you had a limitation your network and you could go around, I think, 2 kilowatt level in Montreal.
Okay. Correct.
So we see in industry at least anything around 20 kilowatt is required to just have an idea of hands-on of this thing. Of course, as long as it's in the control side, it is okay. We get a lot of feel of it and do it. But when you go practically in the implementation, there are many issues, and I think it's a great opportunity for me to listen to an eminent person like you, who has worked a lot in this area and who is pioneering more efforts in IEEE. And you're leading light to many people, both in the technical field and the IEEE field. I'm very happy to be associated, and I hope all others have taken benefit of it. I think we can listen to them. And thank you very much for your lecture.
Thanks.
And that's excellent. I was looking for the unbalanced control. You have explained that also. Unbalanced load. That also explained, I think, with the 4-wire system and all. I was asking a question. You have covered all the aspects.
So this paper that we wrote, and it's a highly cited, I'll go there one more time. Here.
Maybe you can spend more time with the participants. I just shared my thoughts. So otherwise they will feel that I might have taken more time.
That's okay. It's Sunday here, so I have a lot of time, you know. Yeah. Yes,
if we have some more time, I can come back to you. Or you can come back to me and entertain my questions.
Yes.
There are some more questions.
Yeah. So thank you, sir, for sharing your experience, and then developments happen indigenously in India also. Thank you. Now we'll go with the participant question and answer session. There are some questions in chat box, and I request the participant to post it here, as well as they can unmute and interact with the speaker also. The first question is, how does a power electronic based active filter performance and cost comparison with normal shunt LC filter?
Yes, so basically what Ashok, I think he asked that question, is getting into is can we basically go and do what you call the hybrid filter, like a passive, they call passive filter. So I have done some work on passive filter as well when I was in Montreal. So essentially what you could do, and let me go back to harmonic spectrum, then I like to answer, with visual. Here you go. So I will just put it there and then go here. Where did the right? So if you look at what is happening here for RL load, THD 30%, your requirement from IEEE 519 or other standard IEC and CA and so many others, UL, is that you must go below 5. So what that means, if you look at what are dominant harmonic, 5th, 7th, and all these are odd harmonic, by the way. So if you have balance and load, then usually you don't run into any even harmonics. So essentially there are 5th and 7th, right? So look at what is happening. 5th is touching to roughly in the neighborhood of, I would say, it's 8, right? So yeah, 25 or so percent, and 7th is above like a 10%, right? About 10%. So if you kill these two by passive filter, and then remaining would be less, right? So what I'm trying to say here, that you could design passive filter using like a 7th and 5th harmonic tuned LC filter. Actually, it's not exactly LC, but it's RLC, because you have to have a little bit R component to eliminate any damping, any oscillation that LC elements can produce. So you have to have a little bit, critical, what you call critical damp system. So you have to have a little bit resistance, but it's not like there's a design tricks and all that. There are a lot of papers on that. So you could go after 5th and 7th and reduce them to minimal, and then if you did that, then your next starts 11th, 13th, right? Some people even developed 11th, 13th, and these first 4 dominant harmonic, 5th, 7th, 11th, 13th, and then rest of the things by themselves were in neighborhood of 5%. So you could indeed develop a what you call the passive filter using LCR component. The problem is there that if something changes in the load, right, then it is very difficult for you to go and change it. So imagine that if there's a single phasing happened in your load, or somebody brought in different type of load. Imagine there's a transformer feed and there's a colony, it is fading all. Somebody brought in new refrigerator, or somebody brought in something novel electronic device, and that is introducing different type of harmonics, then that passive filter will not be tuned. In addition to that, the tuning of these is load dependent. If load is changing and deviating too much, then you have to take care of rest of it. So combination of passive and active filter would be a good solution actually. So some people have done work in that direction, because if you look at the 30% harmonic, what that means is actually, so imagine that your load is 100 kilowatt and it is generating 30% harmonics, means it is asking 30% additional current, which are non-sinusoidal, right? So you have to have 30 kilowatt converter, ideally speaking. So if this converter is 100 kilowatt, this need to be 30 kilowatt to be able to compensate. But if you could basically reduce the harmonic here by passive filtering to, let's say, 10%, then all of a sudden the rating of this converter can drop from 30 kilowatt to 10 kilowatt. And if you compensate 11, 13 and put the rating, even 5 harmonics are 6%, then all of a sudden you found this converter is 6 kilowatt rated. So when we are talking about magnitude order difference here, 30 kilowatt versus 6 kilowatt rating. So if you want to use the very sturdy inductor, resistance, and capacitor, then you could do, and then delicate devices, IGBT and all that, which can likely to fail, or silicon carbide, gallium nitride, those switching elements likely to fail, generates EMI, EMC, noise, and all this stuff like that. So you want to handle those one carefully so you can minimize. Another problem with the LC filter is that it is very difficult to find tight tolerance capacitor. AC capacitor are come in tolerance of about 3% to 5% or something like that. And then if you have seen AC capacitor, if they are electrolytic filled, liquid filled capacitor, they like to change their values over time, and then it becomes very, very difficult, right? So inductor can be designed very tight tolerance, but capacitor may not, and then over time those can deviate. So you have to worry about longevity and reliability and all those aspects. That's a good point. People have done, all sort of work. Active advantage of active filter is that you can pretty much control it, right? You can go and just change your control algorithm, and it will take care of the stuff things. So adaptability and reliability and changeability and all that. Certainly, when you have control component, you can change it as you want. But when you have uncontrolled component, you just cannot change it. So things like that you have to basically consider, and then go from there.
Okay. Yeah. So Dr. Shankar, did you raise the hand?
Yes.
Yes, please.
Yes, good evening, Brij Singh sir. It was very informative session. I have one doubt related to the unbalanced system.
Mm-hmm.
Sir, actually, in case of unbalanced system, like after the connecting the active shunt filter, what is our objective is to have a sinusoidal currents, like all the three phase are sinusoidal currents, and they should, is that their magnitude should also be equal?
Correct. Yeah. So when there's unbalance, then basically imagine that these were three-phase unbalanced load. At this point, you would be able to do that, what you call the, actually I may go, I have some slides on that. The reason I did not do, because interest of time, but I can go some of the slide that I have hidden. Let me see, try going. I'm just want to minimize this window, and here you go. So not that, but yes, indeed you could, this I'm developing the theory, and then I have done some work related to still talking about some filtering and all stuff. And here you go. So essentially here what I had was, and it is hidden slide, so I can unhide it and then go from. So what I was doing here was that there were three-phase, so system has only two lines, right? So, and then I as soon as I turn on the converter, then all my three-phase currents are nearly sinusoidal and in phase with the voltage, right? So this is phase A, phase B, phase C. So compensator can do that job, right? So let's say what was going on here was that phase A did not have any load, right? But then as soon as you turn on phase A, also it start like it is behaving like a load, because your supply want three-phase balance load, and then similarly here, right? So this, since it is a current control converter, it will do the job. If there was any non-linear, let's say any upload was non-linear, it will even compensate that. So that paper, this paper that we wrote has all those results about it, talking about various type of loads, and that's why we call it universal control, universal controller, if you will. So it has a lot of, like, even title of the paper is saying active filter, voltage regulation, harmonic elimination, power factor correction, and balancing of the nonlinear load. So if we want to look at that here, indeed that does, but you want to have a 3-phase 4-wire system would be better. 3-phase 3-wire, that's what we experimented here at that time. But 3-phase 4-wire system will do all that job, balancing, taking care of harmonics, taking care of reactive power, turning single phase load to behave like there's a 3-phase load and things like that.
So is that energy, like you mean from one phase to another phase, that power transfer is taking place, sir, after this connection of this active shunt filter? For example, to the phase. Okay.
Go ahead, keep talking.
Yeah,
Sorry,
in case of in case of phase A, previously there is no active power, but because the source is drawing a sinusoidal in phase with the voltage. Therefore, as you said that the currents are sinusoidal with respect to voltage, and all of them magnitudes are same. Means though like active power is not available in the phase A, so that the whatever the power is coming from the phase A will be distributed to the other phases.
Yeah, so let me try answering that here. So imagine this here. What was happening was that I had single phasing, right? So what I did was that this is current, this is voltage current, and then source current, load current, and then this, right? So I basically applied single phasing, right? I killed that one phase load in one phase, then that turned into from this type waveform to this waveform. So essentially compensator is the one that is behaving. So let's go back to basic theory here. I'm just want to bring the diagram here to explain. Imagine that what it is, so like if you apply the Kirchhoff current law here, right? Your aim is that you want to have a sinusoidal current here. So then the sum of this current and this current is making this current, right? So essentially that's what will happen. It could potentially happen that this current could basically circulate back like this to other phases, but essentially all of the phases together will behave that if you do KCL here, then essentially if my objective is that this current need to be sinusoidal and this current whatever it is, I don't have any control because that's what the people are going to put load on, then my controller should basically do magic, if you call it magic, then that is what it trick here, right? So it could happen that this current may be circulating among phases to make it to behave like that. I have not measured it, but it is perceivable that this converter plus this converter together basically will obey the Kirchhoff current law. And if your reference current here are 3-phase balance and sinusoidal current, that's exactly these two converter to this is uncontrolled, this is controlled, they will do. And load you don't want to disturb, right? If you disturb the load, people will be annoyed, right? Imagine that you are a utility company and you are compensating the garbage produced by your customer, then you don't want to annoy them, right? So probably this converter is the one that is doing all the tricks.
Okay, sir. Thank you. Sir, one more continue to the question. Actually, there was a simple voltage source inverter also. With that, at P mod, I mean, if I able to give the current reference, then I can also control the current as a sinusoidal. But here, after a simple diode bridge rectifier, we connected another shunt filter. Like, can you suggest at which applications we can directly go with like a simple voltage source inverter where we can control the currents, like the line currents to be a sinusoidal. And here also, like you are having a rectifier, diode bridge rectifier, and then you will be connecting active shunt filter. Can you suggest us like which applications we prefer to directly use a voltage source inverter where we use IGBT stacks? And here we use a diode bridge rectifier stacks, and then we connect a filter to make the currents to be a sinusoidal. So can you suggest like for which applications we use direct voltage source inverter, and for which application we use a bridge rectifier and active shunt filter?
Sure. So like, for example, those drives, most of the drive that you have, so they have a front end rectification, right? And imagine there is one inverter here, then electric machine control. So they come with that. You can connect your drive, electric drive, right? Like a particularly like an industrial drive, I'm talking, not on the electric vehicle. So then you could basically connect them to supply that you coming, right? So since front end converter is a diode rectifier, and the inverter that would be here is controlling machine or whatever it is, then that's called diode rectifier based system. And you may have RC, most likely it is RC here, RC componentry, means your inverter fed machine is behaving like a resistance, if you will, and there would be capacitance connected here. So it is more or less like emulating the behavior of diode rectifier fed RC load, right? So that is the basically those drives comes. Now they would generate the harmonic. So there are two methods to compensate. One is, of course, you can use the what you call the shunt filter like I have here. Another one, you turn that drive rectifier into control converter, like active rectification. So you replace converter by the active rectifier, that I also call a voltage source converter, right? So that would be one application that you replace the, and then you would have all the harmonics, and because it is going to do active rectification. So it is control elements, switching elements put in this thing are going to shape the current sinusoidal. So that would be one application. We call them actually BSI, right? Voltage source inverter. But essentially, this is also called a BSI. That could also be a BSI, voltage source inverter, right? But it is working in rectification mode or active rectification mode. So that would be one application of such a thing.
Yes, sir. Thank you very much. Thank you. Your session was very informative, sir. I understood few fundamentals basically. Yes, thank you, sir. Thank you.
Welcome.
Yeah. So there are two questions in chat box, sir.
Okay. You want to read it or? Okay.
Yeah, will you explain once more how P tilde is coming and what is the physical significance of it?
Sure. So let me go back to here. I'll just maybe here. So, you know, what we did was that you can measure the power here, right? Power consumed by load using this alpha beta transformation. And then you could decompose these, because if you have a P, right, and you pass it, you do low pass filter, like I did 10 Hertz filter, then you could separate that, because if you have a P, right, and if you pass that P through a low pass filter, then what you get basically P bar, right? And then once you know P and you know P bar, then you subtract, then you get what you call P tilde, right? Like exactly like here. And then, so what is the significance of this? Significance of this is because if you connect the three-phase load, if you connect the three-phase load, you know, which are what you call resistive load, no reactive power, nothing, right? Current are locked in phase with the voltage, sinusoidal shape. And if you do this mathematics, what you will find that Q is 0 actually, and P is actually P bar, right? Why P tilde is coming? Because you have a non-linear load. It has a harmonics, right? And power is pulsating here. So that pulsating real power, that's what the P tilde is. And honestly speaking, if your objective is to have the supply system should behave like a three-phase sinusoidal, you know, R load, like no inductive component, no capacitive component, no nonlinear component, diode, switching element, nothing, then essentially you are seeing you are seeing exactly like this portion, supply and the resistance and nothing else. Right? If you have such a system, then voltage and current would be in phase, right? And then if you calculate P, then it would be P bar. So P tilde is coming because you added all this garbage, right? All this, and you need this because that's what the load is, right? So P tilde is signifying the pulsating nature of real power. And supply doesn't like to supply that. So who would supply a control element, which is active filter in this case?
Okay. Yes, sir. Another last question. It is a comment come question. Very useful for renewable, especially applications of active filters. The only concern, what about the cost that will increase because of active power filter system?
So sometime, let's say utility company has restrictions on you that, and I will tell a couple of history from US. So if they have restriction that you no longer can have harmonics more than 5%, they if let's say there's a mandate by utility company, local government, that anybody putting load on the supply system has this compliance, right? So it's a compliance requirement. Whenever there's a compliance, cost doesn't matter, right? Because compliance means compliance. You have to comply. You cannot go and say, oh, by the way, this is costly and I cannot comply. So compliance has to be met, right? So that's why cost doesn't matter at that point. So I would say that now the question is that what is the low cost solution you could develop to do we comply? So it is utility driven. Actually, I forgot the name. Actually, there was a very senior person. His name was Dr. Srinivas. Now maybe retired in Montreal, and he was working in hydrocubic. I think Dr. Srinivas was from Tamil Nadu in India, but very good friend of mine. I used to interact with him those days when I was in Montreal. So he did some study on the conformal and non-conformal current. So what he thought was that he was developing some criteria that how we go and start charging people extra electricity bill, that if they are not conformal. Conformal means that if you connect a load and you do not disturb my voltage, let's say I'm a utility company and I'm supplying your load, and you connect your load across my lines and you do not disturb my voltage, then you are conformal. But if you begin to restore my voltage, you are non-conformal. And then what is the difference? How much difference you are producing? How much non-conformity you are bringing? That much electricity bill additional you will pay, right? So when there is a compliance problem, then cost doesn't become cost is not a criteria, right? But now the question is that how much, what is the penalty, how much you want to pay for this? That's where engineering solution comes into play. Like we have talked earlier, some, being compliant by many methods, like you do some passive compensation, some active compensation and things like that.
Okay. Yes, sir. Sir, I have one last question from my side. And what are the chances for getting this failure or damage of this capacitor? And what is the reliability of the same capacitor if you install in practical field?
So these capacitor, the capacitor that I connected here, actually Akagi has tested it with the as less as 5 microfarad, and I also tested with 5 microfarad, and I found that capacitor is not needed. Actually, you can run it without capacitor, but the problem is that you need at least some of it. So very small capacitance. Now the question is that what type of capacitance? So I use electrolytic capacitor here, right? But you can go and use film capacitor, and film capacitor have proven reliability. Polypropylene film capacitor, if you keep their core temperature below 65 degrees C, then they last hundreds of years. They're highly reliable. Electrolytic capacitor, have reliability issue, means they're liquid. They have electrolyte inside them, and it evaporates with the heating and over time. So then the equivalent series ESR goes up, and then when ESR from beginning to end goes 3 times, right, then you need to discard it. So if you use film capacitor, then you don't need to worry about reliability of the capacitor. You have to make sure that you don't have exposure to humidity and things like that. As long as you took care of those, reliability is not a problem. Now the question is that failure mode of these capacitor. So if you have a film capacitor, that fails open because of how the film is produced. Polypropylene film is metallized. It is highly reliable. Failure mode is fail open, but electrolytic capacitor fail short. So if you imagine that if you put a short circuit here, you are likely to damage some of the devices. So you need to consider failure mode and all that. Now, film capacitor technology has been matured quite a bit. All electric vehicle and everyone is using those. So I would recommend, if anybody is developing a new active filter, go with the film capacitor. Those will be a little bit expensive as compared to electrolytic capacitor, but they are very good. And another thing is that if you look at electrolytic capacitor, film capacitor, in electrolytic capacitor, you pay for ampere, right? You get microfarad free. In film capacitor, you pay for microfarad, you get ampere free. So you want to see that what is the ampacity of the current you need. If you need a very low ampacity current, right, then probably you want to go for film capacitor, sorry, electrolytic capacitor. But if you want to go for high ampacity needed here, then you want to go film capacitor. So things like that you want to consider. But if reliability is the only criteria, I would recommend go and use film capacitor. It fail open and have a long reliability.
Okay. Yes, thank you, sir. One more question from our friend Sandeep Madsetti, sir. I would like to know how the APF are used to mitigate the renewable energy penetration. As per my knowledge, and energy storage systems is easy to reduce the penetration of effect on utility grid.
Dr. Sandeep, Rajgopal here.
Yes, please. Yes, sir.
After you finish the question, can I get some time to ask a few questions?
Yes, yes, yes. Sure,
If
sir.
it's
Sure.
not a constraint, I would like to take about five minutes.
Yes, sir. We'll take it, sir. Yeah.
Okay.
Sir, this is one question Sandeep has posted in chat box.
Okay. So do you want to read that, or you want me to look
I would like to know how APF are used to mitigate the renewable energy penetration. As per my knowledge, energy storage system is used to reduce the penetration effect on utility grid.
Yep. So one possibility could be that if you look at the energy storage devices, most of them are what you call the, DC type, right? All the energy storage elements are DC type. So one possibility could be that you could add energy storage devices which would be superconducting type devices, or battery, or ultra capacitor and things like that, power energy type devices. And then imagine that this is your source generated by what you call PV, wind, or whatever it is, solar, right? And this is our load. So load cannot go away, but source can go away. So you could basically turn this compensator into called a UPS type thing, right? So this can become your source for whatever number, or if it is brown out or whatever it is, right? Or some shading is happening. Imagine that if it is a PV and it is generating energy, right? There could be some energy storage here as well, or if not, then don't worry about it. I'm just trying to explain hypothetical situation. So imagine this is a PV, and this is your active filter or compensator, whatever you call it, right, at that point. And then there's a shading going on, right? There's a cloud over the panels. then at that point this can kick in and start supplying some brownout situation. Another one, if it's night time, then this can kick in and start supplying your load, whatever minimal load you want to manage at that point. So certainly this converter could be useful to get interface with those renewable energy systems. And renewable energy are, unfortunately, they are not basically 24/7 type source, right? If wind is not blowing, you can't get electricity. If sun is not shining, you can't get electricity, right? So at that point, you have to manage using energy storage interface and then active converter, and then it will basically provide the power during that time. So that would be actually hypothetical scenario I would consider, and I think it is realistic, can be done.
I request Dr. Rajagopal.
Thank you. Sir, I have a few questions and maybe supplementing some points. First, I would like to add that regarding the capacitor, from my experience, these electrolytic capacitors, they're okay if you're using low voltage. We were developing a static converter for railway applications in 1988 using GTOs and all. The DC bus was around 600 volts. And once some commutation failure happened and the blast was, or some high voltage came, it was fantastic. And that too depends on the energy level you're having. See, the DC link capacitor, if I am developing for a 400 kVA inverter, the capacitor on a 2-level inverter will be huge. And railways have this, what do you call, DC, that is panto bounce taking care and all. We had to give some right through and all. So what I'm trying to say is, from that time, the railways informed us, from their learning also, that we should always use these AC capacitors. I think they are called Mylar capacitors, something like that. Name is there. It's quite a long time since. So the reason they say is electrolytic capacitors blast, whereas this AC capacitors puncture through, so there won't be explosion. So safety point of view is very important. You must go for storage applications in DC side with other than electrolytic capacitors. That is what I wanted to supplement. And they also today insist in railways for all the static converters and all, the AC capacitors type, not this. At that time, we were using Elcon makes capacitors here in India. Later on, we also had this, I forgot the name because of aging, certain memory issues. That second one is, today in the railway traction applications, as somebody was talking and you were explaining also, all the electric locomotives and EMUs are having front-end converters. Majority of them are having front-end converters, even metro railways. So all these things are also creating a lot of harmonics into supply side. So this active filter requirement comes, as you said, the regulatory fee insists, otherwise it's not. Next point is, many people do not know, even in steel plants, other places, when there are a lot of failures, it is because of harmonics. One of my friends has done extensive study and has come out, even in data centers where some of this, where people are using non-linear loads, sometimes suddenly things burn away. And ultimately, when he did this, the study, it has come out, it's because of the pumping of harmonics into the distribution networks. Other connected equipment is getting affected. So the significance of it is very much required in the present day active filters. Whether the regulator puts it or not, I think so, in the interest of the end user.
Actually, being being responsible citizen, right? You don't want to drive car in opposite direction to cause accident. So I would agree. Yeah, you want to you want to take why government develops rules, regulation, because people violate law, then government goes into parliament, develops some rule to control people, put penalty on them. If people start following everything, then there's no rule required, because so that's why being a responsible citizen, all that is good idea, right? But when people don't, then regulatory agency are going to regulate it, and regulation is always bad idea, right? It hurts everyone, it hurts economy and things like that. So I would agree.
Yeah, in fact, our experience is when we developed this StatCom and all, we tried to get the three nodal agencies to give us orders, because our R&D was a industrial R&D, new product development and new business development. So when we demonstrated all these things, we want ultimately company says we spent so many crores, now give us business. So at that time when we tried to generate business, see the main benefit of this StatCom, as you know, it is harmonic reduction, dynamic voltage regulation, and one more aspect was there, power factor control.
Yeah.
Harmonics reduction, I mean, we called the meeting of the Transco, Genco, and then this Discom and all. They said, the harmonic reduction, the higher level lies, it is a Transco responsibility. We are not coming to picture in the Discom side at that time. I'm talking around 2000.
Okay.
Today matter things. At Discom level, they said so far we have not implemented any serious regulations. So after developing things with the commercial focus, getting orders even today is difficult. Let me tell you. Unless the regulator puts in certain requirements. Anyway, that's sharing of experience. Sir, I would like to just ask you a slide on this.
Before we go there, so I did implement what you call StatCom, UPQC, UPFC. So Unified Power Flow Controller means between two sources. Like imagine that between between Hyderabad and Delhi, you want to control electricity. You can put UPFC and you will able to control the direction flow, power flow, and everything. So I implemented these. So what I did was the two converter. Of course, these were done 2 kilowatt level, not megawatt. But I was able to change the direction flow of the power. Right, I had two different sources, change them their angle between that. Then I did StatCom related work. It's all reported in those papers that I published. Then I did also SSC, static series compensator. What that means is converter in the can insert a voltage in series between two sources and can alter the power flow. So all that things I did in like from 96 to 99. So I was very much immersed. I was so much immersed in the power quality that if I see any waveform, if you bring a waveform in front of me, I would tell without meter, hey, this is the THD in this thing. Yeah, go ahead, please. Next question.
So just had one doubt, whether I understood correctly or not. Your slide on harmonics, if you show, where you have showed with the various types of methodologies, that 4.9%.
Yeah, this one, not this actually. There was a
that fundamental harmonic, other 7th to 13th.
This one. Yep, this one, right? Or you want to go harmonic spectrum here? This one.
Harmonic spectrum.
Okay, sure.
Sir, if I am seeing this, see the first one, black line shows without any compensation, load current.
Correct.
From your legend, 29.7% TDD. So with the modified direct current control of active filter, supply current has reduced to 10.2% TDD. That is the second type of color.
Yeah, this one.
Light color. Okay. And with the third one, with the indirect current control, the next bar. Then that no color bar is with improved indirect control algorithm.
Correct. Yeah.
This is cost optimized or what?
There's no there's no cost optimization here, because I just changed the so those equations that I developed, right? And I can go back to there, but let's just stay few
Okay,
minutes.
no,
Few
my
seconds
question
here.
is not that. My question is not that. Now, as somebody was asking about the harmonic, fifth harmonic, you were explaining. It is in the, without any compensation, is around 25% or so.
Correct.
So with the first method itself, with modified direct control, where you got 10.22% TTD, the fifth harmonic has come to around 5% or so.
Yeah, nearly that. Yep.
Right. Then with the next color, that is 7.2% TTD1. That's third color one. It is almost equivalent to 4%. And the fourth color, that is with 3.22 TTD version, fifth harmonic is much less. Now, already without any compensation, whatever is there, you have reduced with modified direct current control the fifth harmonic very much. During the discussion, there was some talk on reducing fifth and seventh harmonics.
By passive filter.
If a person uses your modified direct current control, already fifth harmonic and seventh harmonic considerably reduced.
Correct.
Correct? Am I understanding correct?
Yeah, no, yeah, you're right. Yep.
So there is no additional requirement of any supplementary filter exclusively for fifth and seventh harmonic reduction. Am I correct?
Yeah, you're right. Yeah, right. I'll get back to what you're getting. Yeah, please keep talking. Yeah, I'll
That's
answer.
what I was trying to understand. When some question answer was taking place,
Yeah,
there is no requirement for anybody to go for specific fifth, what do you call selective harmonic of elimination of.
Correct.
I'm trying to recollect from the conversation. Selective harmonic elimination method for fifth and seventh harmonic is not required if you implement your modified direct current control, even the first version of the 10.2% TDD version. This is what I'm understanding. Am I correct in understanding?
Correct. You could basically go selective harmonic elimination. So when I answered that question, somebody asked that what if I use ALC filter, right? Yeah, fifth and seventh harmonic or any harmonic tuned ALC filter. And if you did that, then what you need to do, you need to basically put additional, I want to go to diagram. Yeah, here. So you could put a ALC component, and people have done some work actually. So you could basically connect a 3-phase ALC filter here, right? And tune that filter into particular harmonic. And if you did that fifth, and if you did that, then you get exactly, what that I was telling earlier, where the spectrum now. Yeah, here. You will get actually this response, and maybe you may get better than this. Because here, depending upon what I'm trying to do, I'm after all the harmonic. Now, when you are going selective harmonic elimination, then you can even do better than that. It could happen that you can intensify others one, depending, right? Because it all depends that if that filter is tuned and has a resonance at certain harmonics and all that, you never know, right, what it could do. So if it did that, pardon?
Does it give any extra benefit?
Extra benefit.
Already somebody using your modified direct current control method, extra benefit does it give?
Extra benefit is that you can go overall, you can reduce the power rating of control converter, right? So as I said, here you must probably use 30 kilowatt converter, and since it's 29, so probably in that range. So if you want to go after and do 10 kilowatt converter, then 20 kilowatt you can manage by passive filtering, and remaining 10 kilowatt you can do active filtering. So what that is called a hybrid filter. So that can be combination of passive and active. And when you do passive, then you need to do tuned harmonic filter, that you can go passive fifth, passive seventh. And if you did that, then what is remain there is 11th and 13th and 17th, right? These are dominant harmonics. And then of course active filter doesn't care, right? Because it is not tuned particularly harmonic. You can if you want, you can begin to decompose these harmonics into like you need to go a little bit more advanced mathematics. Let me go to quickly to that equation and then I'll answer. So here, that big equation that I had, all four component, I just want to go there. Yeah, here, yes. So what you could do is that you can begin to decompose your power P tilde and Q tilde into harmonic, because Q bar and P bar doesn't have any harmonic because it's DC, right? But you can basically start doing further mathematics and do harmonic analysis on that P tilde and Q tilde. And if you do that, then even you can do your active filter can also turn into selective harmonic elimination. So people have done that type of work also. Selective harmonic elimination by passive filtering, selective harmonic elimination by active filtering. So people have done that work, but it will certainly require lot of calculation, mathematics and all that, right? Which modern day DSP can do the job. So yeah. So that would be the benefit. Power rating reduction would be direct benefit by some harmonic elimination by passive and rest of the by active would be directly benefiting the power rating reduction of these elements, because as we talked earlier, these are the delicate. If something is going to fail, switches are the one that are going to fail. So if you could basically make the switches reliable by operating them at a lower power or reducing their power rating and making robust and all that, then you will make overall solution would be made much more reliable. But the problem is that if you have a passive filter, those are harmonic tuned and load dependent. If load is changing, then again this converter start going to pick up all those so
in this current control inverter which you have presented here, that harmonic spectrum, what is the switching frequency which maximum used?
Yeah, so I use about like a 5 kilohertz.
You have showed the harmonic spectrum analysis, no? That bar chart.
I'll go there.
Whatever values you got with that 3 modified versions, what is the switching frequency maximum that occurred?
So I use, if I remember correctly, I use somewhere from 2 kilohertz to up to 5 kilohertz range. Those were IGBT in those time, and they were good, So I think because it is a 60 hertz system, right? So for 60 hertz system, anything switching in 2 kilohertz to 5 kilohertz is good enough. So, but yeah.
Thank you, sir. Thank you very much, and thanks for extending the talk for answering my questions. Thank you.
No problem. It's a pleasure.
Thank you, Dr. Sandeep.
Thank you, sir. Yeah. So thank you, sir. Actually, I think now we are already crossed 2 hours plus now. If any questions are there, I will correct the questions and I will direct to you, sir. Actually, that's better. Actually.
Sure.
So I think with your permission, we'll proceed to formal vote of thanks for this session.
Before that, sir,
Please,
Dr.
sir.
Sandeep,
Please, sir.
Dr. Brij Singh, when you come to India, please let me know. I'll be very happy to invite you to our chapter and also take you to our PHL corporate R&D and introduce some of my colleagues who have worked on this StatCom and other areas. They'll be delighted to talk to you and learn from you.
Sure.
So
yeah.
I invite you anytime you come this side, please let me know.
And this is Hyderabad, right? I assume.
Yes, Hyderabad.
Okay. Yeah, that's
Ours
a good connection, right? Yeah, good connection. So flight and all that. Yeah. Okay. I'll certainly keep in mind.
Dr. SL, we call him SLN. Lakshminarayana Garu is my guru in IEEE. He is a very knowledgeable person. So earlier we were together. Just recently that has become separate section. So please come.
Sure.
Welcome to Hyderabad.
Sure.
IEEE PS chapter and PELS IAS chapter. Ours is PES, IAS and PELS joint chapter of Hyderabad section.
I see. Sure.
Thank you. Namaste.
Very welcome. Yeah, namaste.
Thank you, Dr. Sandeep.
Thank you, sir. Thank you for joining. Now I request Mr. Dharmendra Kumar, so Chair, NIT AP IEEE PELS for Electronics Student Branch Chapter, so to propose the formal vote of thanks for this session.
Thank you, sir. A very good evening to all the dignitaries of the today's event and all the participants. Before proceeding to vote of thanks, with your kind permission, I will take the opportunity to brief about the future events of IEEE Power Electronics Society Student Branch Chapter of NIT AP, Vizag Bay Section. This IEEE PLS Student Branch Chapter was initiated by all the research scholars of Electrical Engineering Department of NIT AP with the support of our Honorable Director, Professor C.S.P. Rao, sir, NIT AP, and under the guidance of Head of the Department, Dr. V. Sandeep, sir. I would like to reveal the main theme of the IEEE PLS Student Branch Chapter, imparting the modern power electronic technical knowledge and to reveal the R&D pertaining to academics and industries. As part of this SBC, we are going to conduct various events like technical webinars pioneered by high professional technocrats from industrial and economics. And also we will conduct enthusiastic events like quizzes, programs, and the other technical events related to electrical engineering. The further planned programs will be helpful for the BTech, MTech, and research scholars to improve their knowledge in electrical engineering, which plays vital role for their career. Wholeheartedly, we would like to work as a team, and we will make this IEEE PLS Student Branch Chapter in the lights of scintillations. I take this opportunity to seek the institute, chapter, and section support always for conducting these proposed events. With this, I am going to my main task. It gives me immense pleasure to propose the vote of thanks for this event. First of all, being chair of IEEE PLS Student Branch Chapter of NIT, I thank PLS headquarters for sanctioning the distinguished lecture. I thank today's chief guest immensely, Dr. Brij N, Singh, sir, John, the technical fellow and IEEE PLS distinguished lecturer, for accepting our invitation in spite of his busy schedule and joining with us and sharing his views regarding control algorithms for power quality control converters and introducing Power Electronics Society. Once again, thank you, sir. I also thank to our Honorable Director NIT Professor C.S.P. Rao, sir, for continuous support and encouragement to start this IEEE PLS Student Branch Chapter of NIT. And I thank to Chair of IEEE Vizag Bay Section, Dr. Lakshmi Narayana Sadasivani, sir, and P.V. Rajgopal, sir, Chair of Joint Chapter PLS Hyderabad Section. And also, I would like to thank our IEEE PLS Student Branch Chapter Advisor, Dr. V. Sandeep, sir, for continuous support and to initiate the Student Branch Chapter, and also thank to all the faculty and students for encouraging and supporting. I thank all the participants, members of various IEEE Technical Society and Student Branch chapters for attending this program, and non-members and others and who made it grand success. Thank you all. Jai Hind.
Yeah. Thank you so much, sir, for joining. So with this, we'll closing the session. So thanks for sir. Actually, if you are visiting, please visit to our campus, NIT Andhra Pradesh, as well as visit our IEEE Vizag Bay section, as well as requested by Dr. Rajagopal sir, please visit to Hyderabad also. So we'll make the arrangement. Thank you.
Sure. Yeah. I will. My plan is to probably next December, or if COVID situation subsides, to be in India, and I may take some time to come to that place and bring my family and have some time there, see historical places. Last time I was there in 2008, actually, to attend a conference and keynote speech and things like that. So, yeah, I would love to come there, and it would be great.
Yeah. Okay, sir. Thanks for joining, sir. Thank you.
Bye.
Thank you.
Thanks.
Okay.
Yeah. Bye.
Thank you, sir, joining, sir. Actually, Rajagopal sir. Actually, thank you so much. Thank you for your valuable time.
Thank you. Thank you.
Thanks for joining, and we would like to work with you and collaborate with you future programs also. So I'll come back with you, sir. Actually,
you are welcome. Most
thank you, sir.
Most welcome. Anytime, any help you want from me, I'm
Sure,
there.
sir. Thank you. Thank you.
Right.
Yeah, thank you all joining. I'm closing the session. Thank you.